Hi, good evening. Can you hear me?
Yes.
Yeah,
Good evening, ma'am.
yeah, good evening. Okay. I'm audible, right? There is no disturbance, no?
Yes, ma'am.
Okay, thank you. Is my screen visible? Hello? Is my screen
Yes,
visible?
ma'am.
Yeah, thanks.
Yes, ma'am.
Yes, ma'am, it's visible.
Okay, thank you. So, yeah, first question. First, so how was your quiz?
It's good, ma'am.
It's good. So, how
Yeah,
did you like the question paper? Hard, medium, easy?
I would say medium.
Medium? Great. Yeah, I saw the scores. Everybody did well.
Oh, then
I'm happy that people did
scores
well.
are out, ma'am.
Yeah, scores are out. The average was 37.5. So, more or less everybody
100.
did well. So, don't need to worry.
Out of 100.
Out of 50.
Okay.
Yeah. So, yeah, everyone passed the exam. That's another good news. So, I think 25 students wrote the exam. All 25 cleared the exam. So, which is very good.
Hello.
Yeah.
There was a question on conjugate
Yes, yes.
function.
Conjugate.
Yeah.
Yeah,
So
yeah.
that was coming equal to zero.
Uh,
Hello.
what? That is?
I mean, when I was writing some derivation on taking the conjugate symmetry, then I was getting the the function total value equal to zero. So is it a zero value function is even function?
Let me check the question once. So it's been a
Yeah.
while. Let me open the question and see.
Yeah, ma'am. In that question, they have given function plus its conjugate.
Yeah, let me open the question. So, can someone tell me the question if you guys have the question in hand?
Just wait. I'll open it actually. It is uploaded now. Or key is.
Yeah, the key is also uploaded.
Yeah, just a minute. I'll open it. Yeah.
Yeah, I think I should also have it somewhere. Yeah, I have it. I have it with me. So the question is as this. So the question states this: let f of t be a conjugate symmetric signal.
Uh, I think not symmetric. It is asymmetric.
Yeah. So determine which of the following are true. So true for the signal psi of t, which is defined as f of t plus f star of minus t. And the options are A is conjugate symmetric, B asymmetric, see real part and imaginary part of psi of t are even, and D, real part of psi of t is even and imaginary part of psi of t is odd. So these are the options given, and this is the signal that was given. And we are also given that f of t. Someone's mic is not muted. Can you mute yourself? It's giving me some disturbance. Okay. Right. So how do we solve this? So always start with the details that were given. So f of t is conjugate asymmetric signal. So f of t is conjugate asymmetric implies f of t is nothing but negated f star of minus t, right? F of t is conjugate asymmetric. This implies f of t is minus f star of minus t. This is something that we already learned. Now we are given psi of t is f of t plus f star of minus t. Now the first thing to check is psi of t conjugate symmetric or asymmetric? So that's the question. So how do we check that? In order to check that, let's calculate psi star of minus t. What is this? So let's first evaluate psi star of t, which is nothing but f star of t plus f of minus t. Now what is psi star of minus t? This is f star of minus t plus f of t, right? Yeah.
Yeah.
So now what happens to this? So this is simply is there something wrong with what I wrote? I think the answers are not correct. Okay. So this is psi of t, right?
Yeah.
This is just psi of t. Uh,
No, but if you directly consider f star of minus t is equals to minus f of t, then
yeah, so I'm just checking this out. So f star of minus t is minus f of t, and this is minus f star of minus t. Okay, so this is like minus psi of t, and also we are getting psi star of minus t is psi of t. So psi of t is the negated version. Ah, that's what you are telling. Okay, it's turning out to be 0. Okay, so it's the 0 signal. Alright, so I think there's something wrong with the question that I gave. We will reevaluate this question. Thanks for pointing out.
So, the question is that if there is a function with zero value, will it be the even function or odd function?
It's both, I mean, it's both even and odd.
even
Okay, yeah.
it will be both symmetric and
Yeah, it's both
conjugate
symmetric and
symmetric and
yeah,
conjugate asymmetric.
asymmetric. Yeah, so yeah, so maybe we will give 2.5 marks to everyone who attempted this question because all options turn out to be correct in this case. So we will do the re-evaluation for this question, okay? Yeah. Thank you for pointing out. Any questions in quiz paper?
I can I have a question, but see, I'm just thinking because I'll be asking very general question because whatever quiz questions were there, what I realized that if I write a function y equal to a x having the function at plus b.
Yeah.
So all the functions most likely was made around this general expression. So I mean the struggle was like that. If we have a general expression for everything in the given element in the function, I think it can become more easy for us to, I mean, in the exam, to do the, I mean, the calculations with the time what is given. So you
Uh,
are getting me what I'm saying, right?
I didn't fully get it. So what you're telling me is, so did it? I mean, are the number of questions not? Are the number of questions more for the time that was given? So is that what you are telling me?
No, no, it's not. I'm not saying in that way. I'm saying to make it more easy, because suppose if I write a
Okay.
function y equal to t, that is equal to
So,
a
so
into,
the idea
yeah.
is, I think we already gave the easiest of the easy. So it's the easiest paper that we have given you guys. So that much I can say. And another thing, so these things you can solve quickly only if you practice more.
Yeah,
So,
true. I
so,
agree.
so, so you can't just, watch the lectures, solve the assignment problems and go for the exam. There should also be some level of practice from your side. The more
True.
and more you practice, the quicker you do such problems. Okay, so it's with the practice, and yeah, honestly, like there is no brain work for signals and systems. It's always with the practice. So yeah, I don't think the level of questions is hard. It's with the practice. The more you practice, it'll be better for you. Okay.
Yeah.
Yeah. So first question, we will do a revaluation. Yeah. Any more questions regarding the quiz? I mean, you can provide, I think there is some feedback form that was open in your portal. If you want, you can go and give some feedback regarding the quiz questions or the difficulty level you experienced, or if you saw any mistake in any of the questions, or if you felt some of the questions to be, like not okay, all those things you can fill in the feedback form. I'll get to see the response. Okay. All right. So can we start with the, um, yeah, so I think who is it? Subhash, right? Mm, Subhash.
Yeah,
Subhash, so you requested for this MATLAB
yeah,
things, right?
yeah.
MATLAB coding. But after discussion with the team and also with the professor, what I was given, like I was instructed to not to go through MATLAB in the tutorial sessions.
Okay.
Okay, so because this course is not dealing with coding, MATLAB will be separately dealt in some other coding course, MATLAB or Python. So professor is using MATLAB in the lecture videos only for instructive purposes. That's the reason why he is not even showing how to code and all. Okay, so MATLAB is being used only for instructive purposes in signals and systems. So this course is mainly on signals and systems and solving systems. No coding will be taught in the live sessions or in the course. Okay, so this is what I was instructed. So I cannot go through MATLAB tutorials in the live sessions.
Yeah, okay.
Okay, so that is
Yes,
another thing I wanted. Yeah.
yes, ma'am. Regarding the first question,
Mm,
since zero function is the only one which satisfies
mm,
both the conditions
mm.
to avoid
All answers are
confusion.
correct.
Yes, ma'am. But in standard context, to avoid confusions,
Mm,
it has been segregated into conjugate symmetric, ma'am.
mm.
Uh, in the internet, it has been mentioned in this way.
Okay, so zero signals are segregated into conjugate symmetric signals, huh? That's what you're telling me.
Yeah, yes.
Okay, so
But it satisfies trivially
yeah,
the both conditions.
it satisfies. Maybe it is segregated into conjugate symmetric signals, but that's like a special case which should be given to
Yeah,
the
yes,
students earlier. So provided that we did not state this in any of our earlier
correct, yes,
lecture
ma'am.
videos, we plan to give uh, whoever attempted any of these answers will be given. So people who
Yeah,
attempted
yes.
conjugate, so whoever attempted AC or whoever attempted BD will be given answers. Okay. So that is important. At least someone should be in a position to identify A, C options are equivalent and B, D options are equivalent. So at least that much we will test. If somebody only gave A, B, then definitely, we have to think, because these two are also the properties of symmetric signals. So I will check this with the professor how to reevaluate this problem, and I'll get back to you guys in the next live session about this. Okay.
Yes, ma'am. Thank you.
Yeah, all right. Okay. So let's go through the week 5 content. So honestly, like, I should be teaching you guys the week 6 content now already. So the things that are left from week 5 is convolution. The other parts I have discussed in our last lecture video. We discussed different systems and the properties of systems like causal, memory, linearity, time invariance. Yeah, all these properties we discussed in our last live session. So there are also more properties. Let me open my notes. What are the other properties that we discussed? Anyone? Stability of the systems.
Stability of the system.
And what more? Invertibility also we discussed, right?
Yeah.
So all these things we discussed in our last live session. So the pending topic from our previous live session or from the week 5 content, I hope your assignment deadline is coming soon. I requested the team to extend the assignment deadline if possible, but in any case, I request you guys to, finish it off before the deadline that was given to you. Because it's more or less the properties of the systems along with the convolution. It's not a very difficult thing to do because most of the questions that were given in the assignments, I kind of discussed them in the live session. So it shouldn't be very difficult task for you guys to solve week 5 assignment problems. Okay. So, but I'll also put a word to the team to, if possible, extend the deadline by few days. Let's see how it goes. Okay. So the left topic is we also saw LTI systems, which are both linear and time invariant. And there is another nice operator that we thought we will learn, which we usually do not learn during our +2 days. It's the operator on signals, which we call convolution, which we denoted by star. So convolution operator is usually denoted by star. And that is some property that we would like to learn today. It's a very nice operator and very important operator to learn. And there are also a lot of properties on this convolution. Let us also look at the properties of convolution. Okay, so week 6 mostly deals with convolution, properties of convolution, and then the summary of systems. Okay, so convolution is a very important operator. Mostly while doing signals and systems course, not many students will be comfortable in applying or like learning this operator. So I would like to give it more time. So if you guys have any doubts, please feel free to stop me and ask questions wherever you are doubtful. But this is an important operator which is also kind of hard. It's not very as you see it, you have to learn it, you have to practice it, only then you will get it. Okay, so let's start with the convolution operator. So how is this convolution operator defined? So convolution of any two signals x of t and y of t, this is denoted by x of t. I'll go really slow, so please stop me if you guys are facing any difficulty. So the convolution operator is denoted like this. So it is x of t star y of t. This star is the convolution operator. Just like multiplication is represented by either x or dot, we represent the convolution operator by this star. Okay, if you see any two signals being star, being they share the star operator in between them, this implies the convolution. Okay, this is the first thing to remember. And now how do we define this convolution? So that there is a definition for this convolution. X of t star y of t is defined as integral minus infinity to infinity x of tau y of t minus tau d tau. Okay, in other words, what you are doing is, so you are fixing a signal. So on your time axis, you are fixing one signal x of tau, and then for the other signal, so this, so this, so let me call this convoluted signal as z of t. Z of t is defined like this for all t. Okay, so in other words, what you are doing is, so x of tau signal you are fixing like that, and y of tau signal, what you do is you first negate the time axis of the y signal, and then you also shift the signal by t, and whatever the signal you obtain, you multiply this signal with the x of tau signal, and this you do for all t. So professor showed a nice animation video in your lecture videos. If you saw, y of t minus tau will be traversing across the fixed x of tau signal in order for you to get the z of t signal. So I cannot draw the animated picture here with hands, but the idea, I hope you guys would have understood by looking at the animation videos from your lecture videos. Yeah, so z of tau is like, sorry, the convoluted signal is like you fix the one of the signal, and you slide another signal across the time axis, and then you find the overall area of, within the original fixed time axis signal. So that's the convoluted signal. If the idea, if you guys are not able to visualize this idea in your mind, I advise you guys to go and watch the lecture videos professor uploaded, where he showed nice animations in the MATLAB as well as in other videos. He used this MATLAB to show these animations and all. So yeah, so you can watch those videos to picturize what exactly a convolution signal is. Okay, but mathematically the signal is defined as z of t. I'll repeat it as many times as you want, because multiplication or division is something that you remember since your childhood. So from here onwards, you should also remember this convolution operation, like how you remember multiplication, addition, subtraction, all those operators. Okay. So z of t, x of t convoluted with y of t is what? Integral minus infinity to infinity x of tau y of t minus tau d tau. Okay. Any questions with the definition? No questions, right? So how do you find the signal? So Any questions with the definition? If you don't have, I'll proceed with the next part. Hello, I'm audible, right?
Yes, ma'am. Ma'am, could you please explain a little bit more about
Mhm.
the definition?
Okay. So did you watch the lecture videos?
Yes, ma'am.
Did you finish watching the lecture videos, week 5 and 6 both?
Yes, ma'am.
Okay. So the convolution operator is some operator which captures, in essence, um, uh, so this is also, let me think how to tell it in easy way. So this operator is something that captures, uh, if so basically the convolution operates. So you learned LTI systems, right? Linear time invariant systems. So for this, every linear time invariant system, there'll be an impulse response associated with it. So this impulse response is like what you call, the noise of the system or something. Okay. And suppose if you send some information input signal x of t into this LTI system, the output that you see is x of t convoluted with h of t. Okay. So why does this happen is something that is discussed in your LTI systems part of the lecture. Um, what the professor says is any signal x of t can be represented using the direct delta notation as x of tau del of tau minus t d tau. This is something that everybody agrees, right? Why? Because this is something that we already saw in our last live sessions and also in certain practice assignments. So that the integral of x of tau with the del of tau minus t is simply x of t. So any signal x of t can be represented as, the integration over x of tau multiplied with the delta version. So this is like every signal can be represented as the infinite sum of scaled direct deltas. Okay. So now suppose if, okay, h, so I'm just trying to see what professor note in his lecture notes. Okay. uh, so the idea is when you write something like this, and when you not very clear on how to prove that the output is the convolution operator. There is some nice steps which I'm not very confident from your notes. But what one can show is, suppose if you transmit some input signal x of t into the linear time invariant system that has an impulse response h of t, when you transmit this input signal over the linear time invariant system, the output that you receive, y of t, would be x of t convoluted with h of t. In other words, what you tend to see is, you can do such experiments. Take any linear time invariant system and, into that system, transmit x of t as the input signal. And that system has certain impulse response, right? Every linear time invariant system has some impulse response with it. So when you try to transmit some input signal into that system, and if you measure the output signal looks something like this, which has this nice form. And this form, this nicer form, is defined as the convolution of the two signals. Or in other words, when some input is transmitted over the linear time invariant system, which has some impulse response h of t, then the output is the convolution of the transmitted signal and the impulse response of the original system that in which you are transmitting the signal. So that's the whole idea of convolution. Like, how it came in the first place is, most of the real world systems are linear and time invariant systems. And for any linear time invariant system, it inherently carries an impulse response with it. And when you transmit some input signal x of t, the output you tend to receive is of this form. And this form is defined as the convolution of the signals x of t and the h of t. So I don't have a straight away proof on how you get y of t as this form, but I can provide you the proof in the next lecture if you require it. So when you transmit any signal x of t into the LTI system, what you receive is something like this. So x of t is, converted. So x of t signal gets modified into a different signal y of t, which looks something like this because of the inherent impulse that is present in the system in which you transmit the signal. Okay, I can provide a proof on how you get this y of t when you transmit x of t into the system with impulse response h of t. Okay, but I don't have a straight away proof at this point.
Ma'am,
Yeah.
in the lecture, yt is equal to infinity to infinity. It's maybe
That
it's
is an error. It is minus infinity to infinity. That's an error. Okay, that's across the entire time axis. It should be from minus infinity to infinity. I think so. When he's talking about this convolution, in most of the lecture slides, it was defined as infinity to infinity x of tau, but it should be minus infinity to infinity. Okay, so this is the convolution operator. So basically, convolution, the motivation for convolution came from, what if you transmit some signal into a linear time invariant system that has an inherent impulse response? So practically think about this. You have some audio signal, okay? And your mobile may have some audio processor. That audio processor is an linear time invariant system, okay? So it has certain impulse response with it. Now, what is the output, that you should see at the end of the audio processor when the audio signal, was transmitted into the audio processor? So that was the question. And the output that you tend to see is, if your audio signal is represented by x of t, and the impulse response of the audio processor is represented by h of t, then the output of the audio processor would be something like this. That is dependent. So tau, this tau variable, you are actually integrating over time. So once you do the integration, this tau variable won't be there, because you are integrating across the entire tau axis. So this, whatever you see here, would be a function of time, and that function of time y of t is the output signal. And this is now defined, to make it simpler, this is now defined as the convolution operator. And convolution, so if you are given any linear time invariant system, suppose if you are given some other system which is LTI, and if it has an impulse response h of t, so the y of t is simply x of t convoluted h of t. Okay, so, or you know that when you pass x of t and the h of t into a multiplier, what you get is x of t multiplied with h of t, right? And when you transmit x of t into an adder and h of t, you get x of t plus h of t. Likewise, when you transmit any input signal x of t into any linear time invariant system, what you get is x of t convoluted with the impulse response of the LTI system h of t. Is that okay?
Yes, sir.
Yeah. So the way it is defined is x of t convoluted with h of t is defined as minus infinity to infinity x of tau h of t minus tau d tau. And yeah, so this is a function of t. Okay, so this is how, and this is the definition of the convolution, and how to convolve any two signals. Suppose you are given x of t and h of t, how do you convolve them? There are steps to do that. Leave x of tau, so the signal x of tau as it is. For the other signal, first find h of minus tau. So this implies time reverse the signal h of tau. Okay, and the next one is to do a time shift. So after time reversal, do a shift of plus t to the signal h of minus tau, and then multiply this h of t minus tau with x of tau. Okay, and this gives you some signal y of t comma tau. Okay, and now what you do is integrate y of t comma tau across all tau from minus infinity to infinity. To obtain y of t as integral minus infinity to infinity y of t comma tau d tau. So these are the steps you have to follow to find the convolution of any two signals. So any two signals x of t and h of t, the way you convolve them is leave x of t signal, replace t with tau and leave that as it is. And for the other signal, first time reverse the signal, which gives you h of minus tau, and then do a shift of plus t to the signal, which gives h of t minus tau. Now multiply this signal with the x of tau signal. Let me call that multiplication as h of t minus tau times x of tau. Okay, so this I am representing by y of t comma tau. Uh, Note that this multiplication depends on both tau and t. Now what I do is, now I integrate this multiplication across all tau. Okay, all values of tau. So when I integrate across all values of tau, the tau variable itself, it'll be removed because you are integrating across all values of tau. So y of t is nothing but integrating across all values of tau, y of t comma tau d tau. So this is your convoluted signal x of t, h of t. Okay, so to just make it clear, we can solve some simple example. Let's consider x of t is equal to u of t. Okay, and h of t is also u of t. Let's try to find the convolution of this. So find y of t is equal to x of t convoluted h of t. So how do we do this? So y of t is defined as integral minus infinity to infinity x of tau h of t minus tau d tau. Now what is x of tau? That is minus infinity to infinity u of tau, and this is u of t minus tau d tau. What is u of tau? U of tau is 1 for tau greater than or equal to 0, 0 otherwise. So this implies this integration is from 0 to infinity 1 u of t minus tau d tau. Right? Now what is u of t minus tau? Let's see. So we have to find u of t minus tau in terms of tau because you are integrating in the tau domain now. So you have tau, this is u of tau, and then this is u of minus tau, yeah. Now what is u of t minus tau? Can someone say what is u of t minus tau? Is that correct? Hello, am I audible?
Yes, ma'am.
Yeah, can someone say what is u of t minus tau? So u of t minus tau would be 1 until tau minus tau is greater than 0 or t is greater than or equal to tau. So until tau less than t, why didn't we get the previous thing? Because we did the operations in reverse side. Remember what we are supposed to do for u of t minus tau? Tell me the operations, please. So u of t minus tau is first scale u of tau by plus t, and first shift and scale, right? And then scale by minus 1. So what is u of tau plus t? U of tau plus t is minus t. Tau. This is u of tau plus t. Now scale by minus 1. So what will that become? So this is u of t minus tau. Right? Uh, Previously, I did the operations in ulta direction. I first scaled and then tried to shift. That's the reason why I didn't get. So don't mess it up. Always first shift and scale. So when you shift by plus t, this is what you get, and then you have to scale by minus 1, and this is what you get. And u of t minus tau is 1 until tau less than or equal to t, and 0 for all tau greater than t. Right? So let's substitute the same thing here. So so we don't have any signal before 0. So this is 0 to t, 1 d tau. So what is this? So this is t minus 0 for all t greater than 0. If t is less than 0, this integration itself won't be there, because you know uh, this integration is going from 0 to t. So if t is less than 0, this integration itself is not defined. So so this is t for t greater than or equal to 0, 0 for all t less than 0. So what we have seen is u of t convoluted with u of t is nothing but t for t greater than or equal to 0, 0 for t less than 0. In other words, this is nothing but t times u of t, or this is also the ramp function r of t. Is that okay? So how did we do? So we just took the definition of the convolution, applied the integrations properly, tried to see where exactly the signal is defined, and then we integrated accordingly. Okay. So for any example, like this is the procedure that you have to follow. But in order to gain more understanding and more hands-on experience on convolution, you have to practice more and more problems. There are multiple problems in your practice assignments, and there will also be several problems if you look up online, or if you open up any textbook that professor gave you as the reference. In most of the textbooks, like lots of problems will be there on convolution. So take up any problem, it's just the definition. So apply the definition and try to solve. You will learn more and more by practice. Okay. So that is one thing that I wanted to tell. There were several examples given in your lecture videos, also in the assignments. Please try to solve them. If you face any questions regarding solving the assignments, you can let me know. Okay. And another, so going to the properties of convolution. So suppose x of t is a signal that is t1 length long. I mean, suppose x of t is some signal that is defined over a length of t1. Okay. And h of t is some signal that is t2 length long. t1 length, t2 length. Then the convoluted signal x of t, h of t is t1 plus t2 length long. Okay, so that is another property, first one. And second one, convolution operator is commutative. What is commutative property? So when you convolve x of t with h of t, this is same as convolving h of t with x of t. In other words, suppose you transmit x of t into an LTI system with response h of t, the output would be x of t, h of t. Or suppose you transmit h of t into an LTI system with impulse response x of t, the output would be h of t star x of t. So both these outputs are always same. Okay, so that is what we mean by the commutative property of the convolution. Okay, and the next property is convolution is associative, which tells that x of t star h1 of t star h2 of t. I mean, if you convolve h1 of t with x1 of t, and then if you also convolve that with another, so this implies, suppose x of t is passed into an LTI system with impulse response h1 of t, the output you get is x1 of t, sorry, x of t, y of t. Y of t is nothing but x of t convoluted h1 of t. And now when you pass this into another LTI system with impulse response h2 of t, the output that you see over here is y of t convoluted h2 of t. This is z of t. And what is y of t? We know that y of t is x of t star h1 of t star h2 of t. Okay. Now this is equivalent to x of t star h1 of t star h2 of t. So this is equivalent to this. So what do we mean by this? So x of t is passed into a single LTI system which has impulse response. So this is x of t convoluted h1 of t star h2 of t. So what this associative property is telling is, so this is same as passing x of t into two different LTI systems in serial. Is that okay? So this is what associative property is telling, that these two are equal. In other words, the picture that you see here, when x of t is passed into a combined signal which has an impulse response of h1 of t convoluted with x of h2 of t, is the same as passing x of t into two serial systems that those are having impulse responses h1 of t and h2 of t. Okay, so that is what we mean by the associative property of the convolution. Is that okay? Is that okay? Any questions?
Baba.
Yeah. Hello? Hello? Am I audible?
Yes, ma'am, you are audible.
Okay.
Yes, ma'am.
Okay, right. So the next property of convolution is the distributive property. Convolution is distributive. In other words, x of t convoluted with 2 plus h2 of t is same as x of t convoluted with h1 of t plus x of t convoluted with h2 of t. Or suppose x of t is passed over an LTI system, okay, which has impulse response. There's an adder here, h1 of t, h2 of t. So when x of t is passed into this LTI system, the output is x of t convoluted with h1 of t plus h2 of t. Now, when I pass x of t into an LTI system with impulse response h1 of t and the same x of t into another LTI system with impulse response h2 of t, the outputs obtained here are x of t convoluted with h1 of t and x of t convoluted with h2 of t. So when I add these two signals here, what I get is x of t convoluted with h1 of t plus x of t convoluted with h2 of t. So these two signals are again equivalent. In other words, these two blocks are again equivalent. So this is what we mean by the distributive property of the convolution. Okay, and the next property is, suppose if you convolve x of t with a time shifted version of delta function, this is simply x of t minus t. Okay, so this is another nice important property. Or x of t convoluted with delta of t is x of t. Okay, or x of t convoluted with delta of t minus t naught is x of t minus t naught. Okay, so these are with respect to the direct delta functions. You can prove them. The way you can prove is, I can prove the first thing. So x of t convoluted delta of t minus t naught. This is integral minus infinity to infinity x of tau del of t minus t naught minus tau d tau. Okay, so remember our uh, delta formula. So our delta function formula was x of t times delta of t minus t naught is x of t naught times delta of t minus t naught. So using this property and substituting, required values of t over here, one can prove that this integration is x of t minus t naught. It's easy to prove. I'm skipping the things. I mean, we have proved it enough number of times already. So we just have to use this property to show that this is x of t minus t naught. Okay. So this is with respect to the impulse function, and the other thing is the shifting property. Suppose x of t star y of t is some z of t, then if you shift x by t1, and y by t2, then the convoluted function will be shifted by the sum of these original shifts in the original signals. Okay, so this is another nice property. There's an assignment problem on this to prove this. Try it out. If you guys are unable to prove, I can help you out in the proof. Okay. So this is with respect to the shifting of the convoluted signals, and this is all it is with respect to convolution and the properties. If you have any questions with respect to the assignment problems or any doubts in the lecture videos, feel free to ask. I am here for some more time. Okay. I'm audible, right?
Yes, ma'am. You're audible.
Yeah, if you have any questions, feel free to ask, or otherwise we can end the. Yeah, if you guys have no more questions with respect to the assignment problems or anything, so this is the idea of the convolution. Feel free to uh, email me if you have any doubts, or we can also discuss the same convolution topics in the next live session. Yeah, for now, if you guys don't have any more questions, we can end the session.
Yeah, thank you.
Ma'am,
Yeah.
could you please explain linearity and LTI systems once again?
Yeah, linearity, sure. So the linearity property is something like this. Suppose if there is an output associated with the signal x of t, let x of t, when you pass through some system, if this produces you an output y of t, okay, now we call this system, the given system, is linear if you pass linear combination of any two input signals. If you pass through the same system, that should give you an output which is linear combination of the original outputs. Okay, so suppose if you pass x1 of t into this system and it produced you y1 of t, and you pass x2 of t into the system and it produced you y2 of t, when you pass the linear combination of these two systems, that should give you an output that is the linear combination of the outputs. So if this happens, then the given system is linear. If this do not happen, then the given system is not linear. Do you have any specific question you want me to explain?
Yes, ma'am. Take an example of this.
Tell me example. So which one you want me to do?
Yt is equal to t square xt plus c.
So suppose if this is your example, let's see now what happens. When you pass x1 of t into this system, the output is t square x1 of t plus c. When you pass x2 of t into the system, your output is t square x2 of t plus c. Now let's pass the linear combination of these two signals, p x2 of t. What should the output be? That is t squared. So let me call this x3 of t. So when I pass x3 of t, the output should be t square x3 of t plus c. And what is x3 of t? A times x1 of t plus b times x2 of t plus c, which is a t square x1 of t plus b t square x2 of t plus c. Now let's try to evaluate a y1 of t plus b y2 of t. This is a times t square x1 of t plus c plus b times t square x2 of t plus c, which is a t square x1 of t plus ac plus b t square x2 of t plus bc. Clearly this, let me call this star and this as star star. Clearly when you pass a times x1 of t plus b times x2 of t into the system, the output is a t square x1 of t plus b t square x2 of t plus c, which is not equal to a times y1 of t plus b times y2 of t. Hence, the signal y of t is equal to t square x of t plus c is not linear. Is that okay? Is that okay? Hello? Hello? Am I audible? Hello?
Yes, ma'am, you are audible.
Yeah. Who asked me this question? Why is there no response? Is this alright?
Sorry, ma'am, I was just disconnected, so I did not get properly.
Okay. So the idea is when you pass x1 of t into the given system, you receive some output y1 of t, which is t square x1 of t plus c for this system. And when you pass x2 of t, you receive some output y2 of t. Correct? I need some response from your end. Otherwise, I don't know whether I'm
Ma'am,
audible or not.
explain with starting. Ma'am,
Hmm?
please explain with starting from.
Yeah, I'm explaining it from the beginning. So this is your given signal. Please respond back, okay? Otherwise, I don't know whether I'm audible or not. So this is the given signal. To find if the given signal is linear or not, first transmit x1 of t, and then you receive a output y1 of t, and then you transmit x2 of t. So you will receive an output y2 of t. Okay? And till here, is that okay? So when you transmit x1 of t, y1 of t is t square x1 of t plus c. When you transmit x2 of t, y2 of t is t square x2 of t plus c. Is that okay?
Yes, ma'am.
Now what you do is now you transmit the linear combination of these two inputs. which I am calling x3 of t. So linear combination is a times x1 of t plus b times x2 of t for any ab. ab can be anything, some constants ab. Okay. Now when you transmit into this signal, the output, so this, if I call it x3 of t, then the output would be t square x3 of t plus c. Correct? Are you with me?
Yes, ma'am.
Now what is x3 of t? x3 of t is nothing but a times x1 of t plus b times x2 of t. Right? And when you just multiply and see, like do some simple algebra, so this is a t square x1 of t plus b t square x2 of t plus c. And also we have y1 of t and y2 of t. Now let's see if this is equal to a times y1 of t plus b times y2 of t. So let's try to evaluate a times y1 of t plus b times y2 of t. What is this? So a times y1 of t is a times t square x1 of t plus c plus b times y2 of t is b times t square x2 of t plus c, and this is simply this, again using some simple algebra. And you can see that when you pass the linear combination of inputs to the signal, whatever the output you obtained, this is not equal to a times y1 of t plus b times y2 of t. So when you transmit the linear combination of the inputs, this system will not give you the linear combination of the outputs. Hence, the given signal is not linear. Is that okay? Is that clear?
Yes, ma'am.
Yeah. Okay. Any more questions?
Explain LTI system, ma'am.
LTI system is known as linear time invariant system. Who is asking me these questions?
Satyam, ma'am.
Okay. So LTI system is linear time invariant system. Any system that is both linear and time invariant is called an LTI system. Okay. And it has an impulse response h of t. And suppose if the output of the LTI system is given something like this, x of tau, h of t minus tau, d tau. From this, one can also find the impulse of the linear time invariant system. Suppose you are given the input and suppose you are also given the output. So from output and input, one can also find the impulse of the LTI system. So LTI system is any system that is both linear and time invariant. And what is time invariant? If you remember, suppose when you transmit x of t, you get y of t. Now transmit x of the delayed version of the input. Okay, so this will give you some output which I am calling y1 of t. And now delay this output y of t by t naught. If the delayed version of the input gave you an output which is also delayed version of the actual original output, then this is called a time invariant system. Any system that is both linear and time invariant is called an LTI system. I think we already discussed in our last live session. So every LTI system will be having an impulse response h of t and x of t transmitted over any LTI system with impulse response h of t will yield an output that is the convolution of the original input times the impulse response. So that is all with the LTI systems. Understood?
Yes, ma'am.
Yeah. Any more questions?
No, ma'am.
Yeah. It's all with the practice. So I request everybody to please practice as many problems as possible with respect to the convolution. And if you have any specific question with respect to the convolution problem, please email me, or we can also discuss in the next live session. And from the next week onwards, we are getting into the transforms, and without knowing the convolution operator, it's very difficult to understand the next parts of the course. Okay, please practice convolution as much as possible. Okay, with that, can I take leave for today? I need some response. Do you guys have any questions?
No.
Yeah, if you guys don't have any questions, we can end today's live session. Okay.
Okay, ma'am.
Yeah, thanks for attending. Yeah, I'll see you guys on Saturday. Yeah, thank you.
Thank you, ma'am. Good night.
Yeah, good night.